Hello everyone, I'm Jimmy. I'm very excited to be here to introduce our work, OptFuzz, Optimization Path-Guided Fuzzing for JavaScript JIT compilers. The JavaScript JIT compiler is a core component of the JavaScript engine, and JavaScript engines are widely used in various applications, including web browsers, PDF readers, and so on. The JavaScript engines can execute JavaScript programs. As a core component of JavaScript engine, the implementation of JIT compiler is inherently complex and incorporates various optimizations such as CSE, LICM. The complexity of JIT compilers has made them potential hotspots for vulnerabilities within JavaScript engines. In recent years, vulnerabilities have frequently emerged in JIT compilers. Most of these vulnerabilities share a common cause. The optimization is triggered, and there is an error in the optimization. So the next question is how to find bugs in JIT optimizations. Maybe edge coverage guided fuzzing. In edge coverage guided fuzzing, if a test case executes to a new edge in the JavaScript engine, it will be preserved as a seed. The purpose of edge coverage guided fuzzing is to explore more code. But we found that merely exploring new code is inefficient for finding bugs in the JIT optimizations. We have analyzed JIT optimizations in mainstream JavaScript engines, proposed the concept of optimization paths, and summarized 3 observations. First, I'll introduce the concept of optimization paths. After analysis, we found that each optimization contains a large outer loop. This outer loop traverses the IR at a specific granularity level, for example, basic block or instruction. The figure on the left is the code of CIG simplification optimization in JavaScript core. Line 8 contains an outer loop that traverses each basic block and triggers the optimization if a specific condition is met. The optimization being triggered means that the program executes to the location where the code transformation occurs. For example, line 3 and line 5. Now, we introduce the concept of optimization paths, which refers to a code execution path within the outer loop, leading to the location where the code transformation occurs. The path in the yellow box is an optimization path from line 9, 11, 14, 15 to line 2 and line 3. Based on optimization paths, we summarize the 3 observations. The first observation is entering optimization is not equivalent to triggering optimization. During JIT compilation, each optimization is executed. However, not every executed optimization will actually result in code transformation. Engine designers often design optimizations specifically for certain patterns in the JavaScript programs. So multiple conditions must be met for triggering the optimization. The second observation is that the test case which triggers a new optimization path may be missed in edge coverage guided fuzzing. The execution of some optimization paths will potentially cover all the edges of other optimization paths because of code reuse. For example, the first 3 paths shown in the slides will cover all the edges of the 4th path. Consequently, in edge coverage guided fuzzing, even if a specific test case triggers a new optimization path, it may not be preserved as a seed due to its failure to reach new edges. In this way, edge coverage guided fuzzing may overlook underlying vulnerabilities related to this optimization path. The third observation is imbalanced testing for optimization paths. Some optimization paths with easily satisfied conditions undergo more testing during fuzzing, while those with challenging conditions are tested less. Based on these 3 observations, we come to an insight. When performing fuzz testing on the JIT optimizations, it is crucial to not only test up to the optimization, but also to comprehensively test the optimization paths within the optimization. So, can we use the optimization path as feedback to guide fuzzing? Optimization paths ensure that optimizations are triggered, and if a test case executes to a new optimization path, it will be preserved as a seed. For the issue of imbalanced testing of optimization paths, we can design a seed scheduling strategy. However, there is a problem when we use optimization paths as feedback. There are nested inner loops in the optimization path. The loop on line 19 is a nested inner loop. Different iterations of these nested loops will result in different optimization paths, which will lead to the explosion in the number of seeds. To solve this problem, we ignore nested inner loops in the optimization path and propose the concept of optimization trunk path. Optimization trunk path, or OPT path for short, represents a path within the outer loop, which ignores the nested inner loop. The first path in the slides is an OPT path. It is worth noting that the second path is also an OPT path. Unlike the optimization path, this particular OPT path does not trigger the optimization. Instead, it proceeds to an early exit branch. For example, line 10. We'll discuss this later. Based on OPT path, we introduce a new seed preservation strategy. If a test case triggers a new OPT path, it is preserved as a seed. In addition, we introduce a new seed scheduling strategy. We implement a two-tier seed queue based on the numbers of times the OPT paths have been tested, such that the OPT paths that are currently tested less will get more chance to be tested. The figure on the left shows the workflow of our fuzzing system. The system consists of two parts, instrumentation and fuzzing. Instrumentation module identifies the outer loop, nested inner loop in the optimization, and mark the start and end points of the OPT path. The fuzzing module is built on Fuzzly. We add a new seed queue to Fuzzly and incorporate a new seed preservation, seed scheduling, and seed trimming strategy based on OPT path. Now we discuss two problems. First, there are early exit branches in OPT path. To mitigate this problem, we use a seed scheduling strategy. This strategy favors OPT paths that have been tested less, while exit branches that have been tested more are not selected for mutation. Another problem is that OPT path ignores nested inner loops. There is a general understanding that when outer loops undergo frequent testing, most of paths within inner loops also receive more testing. There may be a few paths in the inner loops that are tested less. OPT fuzz requires a more fine-grained feedback, but implementing such feedback could introduce additional overhead that we will investigate in the future work. Next is evaluation. We choose 4 SOTA fuzzers, Suprin, Fuzzly, and FuzzJIT, and 4 JavaScript engines for experiment. In terms of bug finding ability, OptFuzz discovered 36 new bugs. 26 of them were confirmed by the vendor, with 3 CVs assigned. In terms of the exploration of OPT paths, OptFuzz can explore more OPT paths than other fuzzers. To evaluate OPT path feedback, we additionally implemented some seed preservation strategies, including N2, N4, N8, and loop paths. Loop paths denotes optimization paths that do not ignore nested inner loops. As shown, there is an explosion in the number of seeds in loop paths. Among various strategies, OptFuzz yield the fewest number of seeds, but found the most number of bugs. Finally, conclusion. This paper summarizes 3 observations. Entering the optimization is not equivalent to triggering the optimization. Edge coverage guided fuzzing may overlook test cases that trigger new optimization paths. And the third one, imbalance testing for optimization paths. Based on these 3 observations, we present first optimization trunk path guided fuzzing, OptFuzz. Through extensive testing, OptFuzz found 36 new bugs in 4 mainstream of JavaScript engines. That's all. Thank you.